For 30 years, a computer rack could shed about 30 kilowatts of heat, because that's all the moving air could carry away. A single rack of AI chips now runs past 130. We didn't out-engineer air, we drove straight off its cliff. And the way back was strange. They fixed it by letting a liquid boil, on purpose, right on top of the chip. Last time we followed the power. A single AI data center pulling more electricity than a small city, and a grid that was never built for it. We ended on a wall. At the density of a modern AI chip, moving air physically can't pull the heat out fast enough. The fans lose. This is the other half of that story. Every watt of electricity you push into a chip comes back out as heat. Every single one. A 1000 watt chip is also a 1000 watt heater. The difference between it and a space heater is that the space heater is allowed to get hot, and the chip is not. Let the heat build up, and the silicon cooks itself. So the entire race now hangs on one unglamorous question. How do you get the heat out? Faster than the machine makes it. 3 steps down. First, why air broke. Then, what replaced it. And finally, the version that sounds insane until you feel the physics. Start with your hand over a stove burner. That's heat spreading over maybe the size of your palm. Now shrink it. Take that heater and squeeze all of it into a patch smaller than a postage stamp. A top AI chip pours out over 100 watts through every square centimeter of its surface. That's not warm. Picture 10 stove burners going full blast, and then crushing all of them down into a patch the size of a postage stamp. So why can't a fan handle it? Because of what air actually is. Air is almost nothing. A room full of it weighs about as much as a large dog. The same room filled with water would weigh as much as a small car. Air is mostly empty space, and empty space is a terrible place to store heat. To cool with air, you blow it past the hot part and let it carry the heat off. But each puff of air can only grab a tiny bite. So the only way to move more heat is to move more air, faster and faster and faster. Do the math for one of these racks and the number gets absurd. To haul 130 kilowatts away with air alone, you'd have to blast it with wind closer to a permanent gale than a fan, non-stop, forever. At that point, you're not designing a cooler anymore. You're building a storm inside a metal box and screaming past every hard drive in the room. That's the wall. For decades, a rack topped out near 30 kilowatts because that's where air quietly gives up. Engineers weren't lazy. They were pinned against a property of the gas itself. Then AI chips walked straight past 30, past 60, up toward 130, and kept climbing. The fan didn't get worse. The problem outgrew the fan. So you stop trying to carry heat in something empty and start carrying it in something dense. Remember the weight? A given amount of water outweighs the same amount of air about 1,000 to 1. And it holds heat far better pound for pound too. Put those together, and here's the number that changes everything. Push a liter of water past that chip, and it carries away roughly 3,500 times more heat than a liter of air. 3,500. That's the whole ball game. Same space, same speed, thousands of times more heat gone. You feel this every summer. Stand in 35-degree air and you're uncomfortable. Step into 35-degree water, a warm bath, and it feels shockingly hotter, fast. Same temperature. The water just pours heat into you thousands of times quicker because there's so much more stuff touching your skin. So the fix, at its simplest, is a cold compress for the chip. They press a flat metal block right onto its back. Engineers call it a cold plate, but picture a cold spoon laid on a fever. Thin channels run through it, and coolant flows through those channels, a few millimeters above the silicon. The liquid touches the hot metal, grabs the heat, and carries it out of the box before it can pile up. A cold compress on a forehead, except the water never stops moving and the fever never breaks. The warmed liquid runs out to a heat exchanger, basically a radiator like the one in a car, dumps its heat, cools back down, and loops around to do it again. The chip stays alive, not because it got colder, but because the heat has somewhere fast to go. This is direct-to-chip liquid cooling, and it's already why those 130 kilowatt racks can exist at all. Air couldn't, water can. But even water running past a hot plate has a ceiling, and the newest chips are shoving on it. So engineers reached for the oldest cooling trick your own body already knows. Your body's best cooling trick isn't blowing air, it's sweat. When a drop of sweat evaporates off your skin, it doesn't just warm up and leave. It changes state, liquid to vapor, and doing that swallows a huge slug of heat in one shot. Far more than simply warming the water would. It's why stepping out of a pool in a breeze makes you shiver even on a hot day. That phase change, liquid becoming vapor, is the most powerful cooling move in ordinary physics, so they brought it to the chip. It's called two-phase cooling. Instead of just running liquid past the silicon, they let the coolant boil right on its surface. Tiny bubbles form directly on the hottest spots, tear away, and carry off far more heat than flowing liquid ever could, for the same reason sweat beats a fan. The chip is being cooled by a controlled, microscopic boil. And the liquid isn't water. It's a special fluid that doesn't conduct electricity, so it can touch live circuitry and nothing shorts out. Which opens the door to the version that looks completely unhinged the first time you see it. Take the whole server, board, chips, memory, everything, and lower it into a tank, switched on, running at full load, fully submerged in that fluid. No fans, no air at all. Just a machine, working hard, quietly bubbling underwater. It sounds like the last thing you'd ever do to a computer. It's actually the cleanest expression of the whole idea. Surround the heat with something dense enough to carry it, and let physics do the rest. Now the final twist, the one that turns all of this on its head. You'd assume the goal is cold. It isn't. NVIDIA's newest platform, Rubin, is designed to run its coolant hot, around 45 degrees, hot tub warm, on purpose. Why would you deliberately run your cooling loop warm? Because if the liquid leaving the chips is already hot enough, you can dump that heat straight into the outside air with simple outdoor dry coolers, and in many climates, skip the giant mechanical chiller altogether. Jensen Huang put it plainly, at 45 degrees, no water chillers are necessary. We're basically cooling this supercomputer with hot water. Those chillers are enormous. In older facilities, cooling could eat up to 40% of the entire electricity bill, the exact overhead the best modern sites had already crushed last time. Skip the mechanical chiller, and you claw back a real chunk of what's left, and stop evaporating a lot of water while you're at it. Run the machine hotter, spend less energy cooling it. That's the move. So here's what actually happened. The industry didn't beat the heat. You can't. Every watt in still comes out. What they changed was what carries it, from the emptiest substance around to a dense liquid to a liquid allowed to boil. Last episode's lesson was, it's not chips, it's electrons. This one lands one layer deeper. The chips were never really cooled by cold. They were cooled by whatever could haul the heat away fastest. And for AI, air was never going to be it. The fans lost. The plumbing won. But notice what we just did. We ripped the heat out of the chip and shoved it into a loop of hot water. That heat didn't vanish. It never does. It's still there, hotter and more concentrated than ever, and now it has to leave the building. Next, where a city's worth of waste heat actually goes, the cooling towers, the rivers, and the strange plan to sell that heat back to you. That's the next layer down. Subscribe and it'll find you.